Hello, welcome to our channel again. Suraj here, and today we are going to discuss about the third part in the Lagrangian mechanics, which is the D'Alembert's principle, and this is the more fundamental than the virtual work. Why? So we are going to see here, and one of the most important thing about the D'Alembert's principle that I've written here is the dynamics to static. This is a very important thing and I'm going to explain it, and it is very fantastic if you understand it, and it is going to be very interesting that what is the meaning of saying here dynamics to statics, and that's the major figure that the D'Alembert's principle does in the Lagrangian mechanics. So without wasting our time, so let's start our today's video on the D'Alembert's principle. So first of all, what is the difference between the principle of virtual work and that is the D'Alembert's principle? So the principle of a virtual work is simple, can be expressed in this form: Fi into the virtual displacement, I will say del Ri, is equals to the zero. Okay, so this is the thing that what's the principle of virtual work here, and this is very important while solving the static problem. It is more fundamental in solving the static problem. But what is the D'Alembert's principle? So first of all, let's derive the D'Alembert's principle, then discuss about that what exactly this is. So let's see here. How can I define the force on some particle? Let's say force is the change in momentum, Pi dot. Remember, a dot sign is very important, and if you don't know, this particular dot represents the time derivative of the any quantity. So if there's I write is there's a momentum dot, this is means it is the time derivative of the momentum, and this is a neat way to write down the derivatives. Okay, now let's move toward it. So we can write the force is equals to the time derivative of the momentum, and this is what exactly this. So for this, let's imagine a Cartesian coordinate to understand in a much more good way. Suppose that I have made a particular Cartesian coordinate, and suppose that the particle is likely to be here. So use some another color. Okay, likely particle to be here. So I draw the position vector at this particular point. It is x and y. Okay, we draw it, and suppose that there is a force acting on this particular particle, and it changes its momentum from p initial to the p final, and initially maybe it in a rest, I will assume. So it changes its momentum. Okay, how can I write this? This is equivalent to the F is equals to the ma in the Newtonian mechanics, but it is somewhat some different. So let's see what exactly the difference is. Okay, so can I put it in this particular left side, and it will become Fi minus time derivative, which is Pi dot, is equals to the 0. And now what I will write is here is Fi plus here minus Pi dot is equals to the 0. Now you will ask that why I put the plus sign here and the negative sign in the bracket. So now the main thing in the D'Alembert's principle came. First of all, हम लोग इमेजिन कर लेते एक सिचुएशन की एक पार्टिकल है कार्टेशियन कोऑर्डिनेट, उसके ऊपर एक फोर्स लगा F force, and you know we can break down the F force. F we can break down our Fi as the force that is acting on the particle. Let's denote it with Fa, and plus the force of constraint. Okay, but we will do this in a next part. When we break down this, we'll do the next part, but for now understand, suppose it is a particle which is a xy is coordinate, and there is a force acting on a particle, and if there is a force acting on a particle, the momentum changes. Yes, what D'Alembert's principle does is that, you see here, this is a dynamics problem. This is a dynamic problem. What is dynamic? Everywhere there is a motion, then we saw that this particular is the dynamics. Dynamics is the moving objects, how to govern the moving objects thing, and that is the dynamics. While in a static, the object is not moving. So what D'Alembert's principle does is that in this situation, the situation is dynamic, but is convert the situation into static. It converts the situation into static, and now what we are left is to only solve with the equilibrium static problem that we does in the virtual work. How? So let's see here, the particle is there, and there is a F force acting on that particular particle, and this F force is equals to the change in the momentum, it's time derivative change in momentum. तो हम लोग ऐसा एज्यूम कर लेते हैं कि उसके ऊपर एक बैकवर्ड में एक नेगेटिव डायरेक्शन में एक यही फोर्स लग रहा है, which is टाइम डेरिवेटिव ऑफ इट्स मोमेंटम, and that's why this force is called the inertial force. Inertial. We assume कि एक फोर्स उसके ऊपर अपोजिट डायरेक्शन में लग रहा है. That's why I put down plus here and the negative of time derivative of momentum. It means a same force which is magnitude is equivalent to Fi acts in the opposite direction to that particular particle here, such that the particles remains in the equilibrium. But this is not happening. This is not happening. But we just convert our problem from the dynamic problem to the static problem. We assume that yes, there is an inertial force acting on that particular particle, which is the time derivative of momentum, which is equal in the magnitude. Here I've written it is equal in the magnitude simply, but opposite in direction, such that it remains in equilibrium, it remains in the static situations. And now we are left only with the solving the static problem. And this is how the D'Alembert's principle changes from dynamics to static. Here, this is not the general form of the D'Alembert's principle. I have just explained it, that we assume that there is an opposite direction force is acting, which is equal in the magnitude of Fi, which is the time derivative of momentum. And that force is keeping that particular particle I have drawn here, P, let's say P, in the rest. And that is the main thing in the D'Alembert's principle. And that's why we want a general equation which is more fundamental than our principle of the virtual work. Because principle of virtual work is only mainly used in the static problem, but this problem, D'Alembert's principle, can be solved that when there is a dynamics, it converts the dynamics to the static. Here is dynamic happening. Here is the particle changes its momentum. But we assume that yes, there is an opposite direction force, that's called the inertial force acting on it, which is making it an equilibrium. But actually it is not in equilibrium. We assume that there is an inertial force acting on that particular particle, which is keep it rest, because the Fi force you applied is equals to the time derivative of the momentum. I already understand the main consequences in the D'Alembert's principle, but so let's see and derive the more general form of the D'Alembert's principle. How we can just expand this. So here, can I take the summation, because there is n number of particles from I is equals to the over I summation, we can take I is equals to the 1 to the n number of particles, and Fi minus P dot I is equals to the 0. Now if you remember principle of virtual work we have discussed here, that Fi del Ri is equals to the 0. But here there is Fi, but also the time derivative of the momentum. So now multiplying our equations both side with our arbitrary virtual displacement, what we get is that summation over I, and which is Fi dot del Ri minus summation over I P momentum time derivative into del Ri is equals to the 0. Now the thing that you are left with is called the D'Alembert's principle, and this is a very fundamental equation. And this is how I explained before that why we are saying that it converts the dynamical problem to the static problem. Now you understand that why it converts. It imagines an inertial force, time and momentum that acts on it so that it remains in rest. But you will understand this particular principle more deeply if you do the examples of it. So now let's move to the solving basically the examples, because examples can generally enhance your understanding of the particular topic. So this is the general D'Alembert's principle, and I'm going to highlight this because this is very, very important for you. And this is the equation that is more arising, and we are going to prove the Lagrange equation using this particular principle, because this particular principle is not much more fundamental, because here okay, let's in the next video we'll discuss about it more deeply, because this is very interesting, and I think in the next video maybe we are going to discuss it in a great detail. So remember, this is our the most important principle, D'Alembert principle, if I'm pronouncing it right. D'Alembert principle. Okay, there is a one more thing, that why to use the D'Alembert's principle, why to use the D'Alembert principle over the virtual work. And why to derive the Lagrange equation? If you have this particular thing, then why to derive the Lagrange equation? First thing is that if you remember that here the arbitrary displacement del Ri is directly connected, sorry, is directly connected to the constraints, but we want an equation which is free of constraints, and what is called the Lagrange equation. Lagrange equation is all dependent upon the generalized coordinate qk, generalized coordinate, not on this, that's why there is a need of the Lagrange equation. In the next video, if you see in the Lagrange equation, let me write it, okay, let me write it so that you can understand it in a more good way, that why to use this. If you can't understand that what exactly the use is, then it's not a matter that you understand it in a deep way. Here you can see that in this particular equation, this contains this equation is not free of constraint, because if it's free of constraint, when we talk about the generalized coordinate, it means I have to convert this all the coordinates del Ri with the generalized coordinate, and that's what the Lagrange equation do. And the general Lagrange equation is I will write it d by dt of the del L divided by del Qk time derivative dot k minus del L divided by del Qk is equals to the 0, here it is L, where L is the Lagrange, and it is equals to the total kinetic energy minus potential energy, so this is the particular equation of the Lagrange. And you see that, have you find the Ri here? No, there is no Ri there. This equation is wholly in the terms of the generalized coordinate, and that's why there is a need of the more fundamental equation which is dependent only on the generalized coordinate, and what this Lagrange equation is. And hope to understand that what is the need, क्योंकि यहाँ पे हमने देखा कि यहाँ पे ये जनरलाइज्ड कोऑर्डिनेट के टर्म्स में हमारा ना डी एलेम्बर्ट्स प्रिंसिपल है, ना कि हमारा वर्चुअल वर्क का प्रिंसिपल है. तो डी एलेम्बर्ट्स प्रिंसिपल का मोर एक्सपैंड फॉर्म, मोर एडवांस फॉर्म है हमारा Lagrange इक्वेशन, जहां पे हम लोग wholly talk करते हैं only about the generalized coordinate and nothing else than the generalized coordinate. Okay, so now let's move some of the examples so that you can understand it better. And one of the example is this. So let's do some examples question. Okay, this question is like a pulley mass system. Okay, so let me draw it. I think this question is I have done this question earlier with the help of the virtual work also, and now you can do this with the help of the D'Alembert's principle also. Okay, this is the particular hour. Okay, here I have drawn a pulley. Okay, and sorry, here I draw a pulley. Here to draw a pulley here. Okay, not a very good definition. Okay, no problem. Here is a mass and oh, the drawing is terrible. Okay, no problem. Okay, let's draw it. So this is a pulley attached to the upward of this particular block, and there is another block which is like this. Okay, so we want to find the equilibrium condition. Suppose that the mass is m1 and its mass is like m2. Okay, this mass is like m2 and m1, and friction is negligible, because if there is a friction it becomes more complex, and the surface is frictionless and the pulley is also massless, and we have to find out the equilibrium conditions for it. And if I remember, it is like the sine theta must be equals to the m2 divided by the m1. Okay, so this is the case that you have to prove down, and exactly this we have proved down with the help of the principle of virtual work, but we can also prove it with the help of the D'Alembert's principle also. Okay, now what we can do is, first of all, let's make a diagram, free body diagram of this particular things. If you think it carefully, that the m1 mass is there and there is an m1g force acting on it. in the downward direction, and in upward direction there is a tension force also. But we know we have to do not include the tension force because Lagrangian mechanics just remove the problem of the constant force. I've discussed in previous video also how. Okay, you can watch it. I put it in the description box. And this is another mass. This is another mass m2, and you can see that here it mg, and this angle is theta. Okay, I have forgot about that. This angle is theta, and there's a mg sine theta force acting on it. These are the particular type of forces acting on it. Now, looking here about the principle of the D'Alembert, we can write it here as summation of Fi dot del Ri. Okay, we have to find out this, and the negative of this Pi dot del how I can do, okay, del Ri is equals to 0. Now we have to find out all the things and finally prove this. So here we have written this, and you know the summation is from 1 to 2 because there is a 2 blocks here. So how can I write this? I can write it as f1 into del r1, okay, f1 into del r1, and plus f2 into del r2, f2 into del r2, minus, okay, now here momentum time derivative is equals to the mass time acceleration. And you know that if I imagine that this particular box is moving with an acceleration a, then this box is also moving at an acceleration which is, then this particular block is also moving with an acceleration a. Now I can write it as oh, what is this here? Sorry for this mistake. 1 minute. Okay, now yes, now as you can see here that f2 into del r2 minus momentum time derivatives is mass time acceleration, and you know that the both objects are the same acceleration, which is mx double dot m1, sorry, and plus m2 x double dot. Now here into sorry, it is del r1 and del r2. I have forgotten about this, and let's write it in a good form. Del r1, there is a mistake. I have not written here, but no problem. Let's write it here. Yes, okay. Let's write it here. Del r1 and del r2. m1 x double dot del r1, and here plus m2 x double dot del r2 is equals to the 0, since the both of the masses are the same acceleration because the string has the same acceleration. Okay, now here how I can expand this? So f1 here, sorry, this is f1 here. F1 force is this, so I can write the f1 force as m1 into the g into the del r1 plus m2 into the g into the del r2 to the del r2, and minus m1 x double dot, and here del r1, and again here minus m2 x double dot del r2 is equals to the 0, and it is del r2, okay, is equals to the 0. Now what I can do is, let's take common of the m1 and the m2 mass where this is. So if I take the common, what I can get is that, okay, m1, sorry, let's take m1 common. What I can find is m1, and here it is g minus x double dot, okay, and here del I, and in the second condition, what I can there here it is m2g. I think I have forgotten about the sine theta, okay, because it's on the block and the sine theta component will be there. And now if I take the common in the second condition, this is m2, and this will become here m2 g sine theta minus x double dot. minus x double dot into the del r2 is equals to the 0. Okay, now here what I can do, yes, now what I can write here, del r1 and del r2, and in my previous video I have also explained about that del r1 and the del r2, which is del r1, sorry here, del r1 is nothing but it is just the negative of the del r2. It is just negative of the del r2. Okay, now here let's see. Okay, m1, sorry, m1 into the g minus x double dot into the del r1, and if I put here the negative sign and to consider right hand side, it is will become the positive of the m2 g sine theta minus x double dot, and here it is del r1. Can I cancel out this? Yes, obviously you can cancel out this. Now okay, and now it is equals to the m1, so okay, m1 here, m1. Now what we're left with is g minus x double dot is equals to the m2 g sine theta minus x double dot. Okay, now what we are going to do, x double dot here, I have forgotten about double dot. Okay, x double dot g minus x is equals to the m2 g sine theta minus x double dot. Okay, now in this particular given situation we are left with this equation. Now we want the equilibrium conditions. So for equilibrium conditions, this is obvious that this particular quantity, let it another pen, which is okay. This particular quantity, which is the is equals to the 0 because acceleration is 0, and because I'm taking about the equilibrium condition, this is equals to the 0, and what we are left with is equations, which is m1, and here g is equals to the m2 into the g, and is a sine theta, and the final what our expression will become here after cutting out the z and g, what are fall with the sine theta is equals to the m1 by m2, and I think we have to prove this sine theta. Okay, sorry, sine theta where it become, 1 minute. Okay, here sine theta is equals to the m1 by m2, and what do we have to prove this? Yes, we have to prove the same thing, but the problem is that here there is a mistake in the subscript, I think, and that's why this thing become, but the general answer is that this is the correct answer of this question. And I hope that you understand the D'Alembert's principle, because in next video we are going to discuss about the principle, or I think the Lagrange equation, and derivation of the Lagrange equation. First of all, to understand the main things in the Lagrange equation, solving problems in the Lagrange equations, and finally the derivation of the Lagrange equation. I hope that you all like the videos about the D'Alembert's principle and doing some problems here. Maybe in the next video we're going to do also a detailed problem on some other double pendulum topics. And you know that this particular question is also done with the help of the principle of virtual work with a very ease. But you know this can also prove with the help of this D'Alembert's principle. Hope that you like the video and subscribe to our channel so that you can get the notifications of different types of the fantastic things in the physics.